Hello, this is Mrs. Sargent, and this is lesson 9.3, the combined gas law. So the combined gas law combines Boyle's, Charles, and Gay-Lussac's laws. And the law compares pressure, volume, and temperature changes. The equation is P1 times V1 equals P1 times V1 divided by T1 equals P2 times V2 divided by T2. And remember, your units must be the same on both sides. So whatever unit of pressure you have on the left, you have to have the same unit of pressure on the right, as well as for volume. And temperature must always be in Kelvin. So if you hold temperature constant, so if you cover up your temperature, you have Boyle's law. P1 times V1 equals P2 times V2. If you hold pressure constant, you have Charles's law, V1 divided by T1 equals V2 divided by T2. And if you hold volume constant, you have Gay-Lussac's law, P1 divided by T1 equals P2 divided by T2. So that's why we call it the combined gas law, because it combines all of those equations together. So our first example problem says the volume of a gas-filled balloon is 30 liters at 40 degrees Celsius and 153 kilopascals. We want to determine what the volume of the balloon will be at STP. Now, STP is standard temperature and pressure. And that temperature is 0 degrees Celsius or 273 Kelvin. And standard pressure is 1 atm or 101.3 kilopascals. So these are going to be effectively our T2 and our P2. We're looking for V2. That's what we need to find. And for T1, we have 40 degrees Celsius. Since we have more variables, I kind of like to make a list of what they are versus just trying to plug them into the equation. It helps me keep everything straight. Also helps me check my units to make sure that I have the same units on both sides of the equation. So we need to add 273 to 40 to get our temperature in Kelvin, which is going to be 313 Kelvin. And then since we have the 101.3 kilopascals, we can use that. So now we're good. Remember the equation. P1 times V1 divided by T1 equals P2 times V2 divided by T2. So now we can just start plugging things into our equation. So P1, I mislabeled this here. Should be P1 and V1. P1 is 153 kilopascals. V1 is the 30 liters. And T1 is 313 Kelvin. P2 is 101.3 kilopascals. And V2 is what we're looking for. T2 is 273 Kelvin. Now, just like we did with Charles and Lusak's law, we're going to do some cross multiplication. So we're going to have 153 kilopascals times 30 liters times 273 Kelvin equal to 101.3 kilopascals V2 times 313 Kelvin. So to get V2 by itself, since everything is multiplied here, we're going to divide by the 101.3 kilopascals and the 313 Kelvin. On both sides of the equation. These are going to cancel out over here. So V2 is going to be 153 times 30 times 273 divided by, in parentheses, 101.3 times 313. And V2 should be 39.5 liters. In our second problem, it says we have a 5-liter air sample, temperature at negative 50 degrees Celsius, and a pressure of 721 millimeters of mercury. We want to determine the new pressure if the temperature increases by 105 degrees Celsius and the volume expands to 7,500 milliliters. So P1 is 721 millimeters of mercury. V1 is 5 liters. And T1 is negative 50 degrees Celsius. P2 is what we are trying to find. V2 is 7,500 milliliters. And T2 is negative 50 degrees Celsius plus 105, since it says that it increases by 105 degrees Celsius. So this is going to be 55 degrees Celsius. And then we need to add 273 to our temperatures to get our Kelvin temperature. And then we need to convert our volume so that it is in the same units. So I'm going to convert milliliters to liters by moving my decimal 3 places to the left, which is going to be 7.50 liters. So now we just need to plug things into our equation. P2 times V2, which is 7.50 liters. And T2 is 328 Kelvin. We're going to do some cross multiplication. So we have 721 millimeters of mercury times 5 liters times 328 Kelvin equals P2 times 7.50 liters times 223 Kelvin. So to solve for P2, we need to divide by 7.50 liters times 223 Kelvin on both sides. It's going to cancel out over there, over here. So divided by 7.50 liters times 223 Kelvin. So liters cancels and Kelvin cancels. So to find P2, we need to take 721 times 5 times 328 and then divide by 7.5 times 223 in parentheses. And you should get 706.99 millimeters of mercury. But we have 3 sig figs throughout in our problem. So we're going to round this to 3, which is 707 millimeters of mercury. And in our last example problem, we have quite a few conversions that we're going to need to do, which will show you why it is kind of important to make that list so you can keep everything straight. So it says a gas at 155 kilopascals and 25 degrees Celsius occupies a container with the initial volume of 1,020 milliliters. By changing the temperature, the pressure of the gas increases to 1,590 millimeters of mercury, and the volume is raised to 1,500 milliliters. What is the new temperature? So P1 is 155 kilopascals. V1 is 1,020 milliliters, and T1 is 25 degrees Celsius. P2 is 1,590 millimeters of mercury. V2 is 1,500 milliliters, and T2 is what we are trying to find. Okay, so we need to first convert our temperature to Kelvin by adding 273. So this is going to be 298 Kelvin. Both of our volume is in milliliters, so we can leave it that way. You can convert it to liters if you would like, but you can, since these are the same units, you can leave it that way. Our pressure units are not the same, and so we need to convert these to be the same unit. I converted both of my pressures to ATM because that's what our conversion factors are to, and you're going to have to end up doing 2 steps anyways to convert, so I just chose to do this so I had smaller numbers. So to convert kilopascals to ATM, we're going to divide by 101.3, and that's going to give us 1.53 ATM. And then for millimeters of mercury, 1 ATM is equal to 760 millimeters of mercury. So 1,590 divided by 760 is going to give us 2.09 ATM. So now we can start plugging things into our equation. So 1.53 ATM is P1 times V1, which is 1,020 milliliters, and T1 is 298 Kelvin. P2 is 2.09 atm, and V2 is 1,500 milliliters. T2 is what we're trying to find. So we're going to do our cross multiplication again, and you're going to have 1.53 atm times 1,020 milliliters times T2 equals 2.09 atm times 1,500 milliliters times 298 Kelvin. So to get T2 by itself, we're going to divide both sides by 1.53 atm times 1020 milliliters so atm and milliliters cancels. So T2 equals 2.09 times 1,500 times 298 divided by, in parentheses, 1.53 times 1020. And you should get 598.6 Kelvin. But in the problem, it asks us to find the new temperature in Celsius. So now we've used our temperature in Kelvin in our equation, and now we need to subtract 273 to get our temperature in Celsius, which you should get 325.6 degrees Celsius. And in sig figs, that would be 326 degrees Celsius for your final answer. You have practice in your packet for the combined gas law, so go ahead and make sure that you work through that. And if you have any questions, feel free to stop in and ask me. Thanks for stopping by. Have a great day.